All right, so let's pick up where we left off last time. We introduced this concept of enthalpy, delta H, and this is a measure of how much heat is either released or absorbed by a chemical reaction. If our enthalpy is positive, that means that heat is being absorbed. We call those endothermic reactions. And if this delta H is negative, we would say that heat is being released, or it's an exothermic reaction. And after introducing enthalpy, we talked about these two ways that we can calculate enthalpy. One is taking these reactions that we know our enthalpy for and combining them to get the enthalpy of our unknown reaction. All right, and then the other way was specifically using these formation reactions here. We can look them up on our constants page, the enthalpy of formation of those of each compound. And we could take the sum of the products minus the sum of our reactants to give us the change in enthalpy of this overall reaction. So as long as you can look up all your reactants and all your products on your constants page, you can calculate your delta H for any reaction. All right, so today we're actually going to just practice both of these methods here. Okay, so again, the first is combining these known chemical reactions. All right, so let's say that we have this chemical reaction. All right, we have our hydrogen gas combining with two iodine chlorines to produce two HCl's and a iodine. So here's this reaction that we're studying. And we do not know the delta H of this reaction. That's what we're trying to figure out here. All right, but we've studied two closely related reactions here. So the first is what happens when hydrogen gas collides with just one of those ICLs. This produces HI and HCl. And we've studied this reaction. We performed this reaction in the lab and we took some measurements, and we know the delta H of this reaction is negative 465 kilojoules per mole. All right, so we don't know anything about this top reaction, but we do know the enthalpy change of this bottom reaction here. And a second similar reaction is if you take HI and combine it with one of those ICLs. You get HCl and iodine. All right, and likewise, we know that the delta H of this reaction is positive 42 kilojoules per mole. All right, so what we're going to do is we're going to take these two known pieces of information and use them to figure out what our enthalpy is of our unknown reaction here. All right, so we have this unknown enthalpy, and then we have these two reactions where we know their enthalpy. All right, and what we need to do is be able to combine these two reactions. We're going to sum up these two chemical equations here. All right, so we're going to sum our chemical equations. So this is how we sum two chemical equations. All right, when we're summing up chemical equations, we're going to create one new chemical equation here. All right, so what I'm going to do is I'm going to take these two reactions here. I'm going to just number them 1 and 2. All right, we're going to combine the reactants of both of these reactions onto our reactant side of our new chemical equation. All right, so now I'm going to sum up these two chemical equations here. I'm going to add them up together. So I'm going to combine my reactants of both of these chemical equations. Onto that reactant side of my new chemical equation. All right, so what do I mean by that? If I look, I'm summing up these two reactions here. So in my new reaction down here, I'll put down my arrow. On my reactant side of this new equation, I want my reactants of both of these chemical equations, right? So I'm just going to copy down everything from equation 1, my reactants, the H2 and the ICl. These are from reaction 1. And I'm going to combine those with the reactants from reaction 2. All right, so I have my reactants from reaction 1 and my reactants from reaction 2. And now I'm going to do the same thing, but with the products side of these two equations. I'm going to sum my products of my two equations into the products of my new overall reaction here. All right, so everybody take a second. Copy down our products. What should that look like on the other side of this reaction arrow? All right, so that means from reaction 1, I have that HI and that HCl. That's all from my first reaction. Then I'm going to combine my products for my second reaction, the HCl and the I2. All right, so when we sum up chemical reactions, we're just going to combine the reactants all into one new chemical equation and combine all our products into one new chemical equation. All right, but then we got one more step to do here, which is to simplify. All right, how do we simplify? If we have two of the same thing on one side of our arrow, so I have two ICLs on my reactant side, I can combine those together to just 2 ICL. Put that coefficient of 2 out front. So I'm going to combine the like compounds on the same side. All right, so if I'm going to simplify here on my reactant side, I'm going to combine those 2 ICLs, right? We got 2 identical matches here. So now my reactant side is H2 gas plus HI plus 2 ICL. All right, if you wrote it in a different order, it doesn't matter, right? The order in which these appear in our chemical equation doesn't matter. We could put the 2ICl out front, same thing. So then everybody take a second and let's do the product side here. Combine any like term that we see on our product side. Nope. So now I have HI gas plus HCl gas, it's plus 2HCl plus the I2. All right, so we simplified first by combining. All right, but in this reaction here, we see that we have HI on the reactant side and HI on the product side. All right, so it's apparently being consumed and produced. That just means it's not actually involved in this chemical reaction. So the last step for simplifying is to cross out anything that appears on both sides of our chemical equation. All right, so we simplify by first combining and then by crossing out our like compounds that appear on different sides of our reaction arrow. All right, so like I said, we have the ICHI on both sides, so that can cross out. And so we see that our reaction simplifies to that same reaction we said at the top we were trying to study. All right, this just matches this unknown enthalpy reaction that we said that we wanted up here. Right, so we didn't know anything about this unknown reaction up here, but we had these two reactions that we did know. We had studied them previously. And if we combine those two reactions, we get our unknown reaction up here. All right, so in the same way, again, because enthalpy is this state function, it doesn't matter if we do this in one step or if we break it up into two steps, our change in enthalpy is going to be the same. So in the same way that we were able to sum up these two reactions to get our unknown reaction, we can also sum up our two enthalpies to get the enthalpy of our unknown reaction. The same way we combine these chemical equations, we're going to combine these enthalpy values here to get our enthalpy value of this unknown reaction. All right, so here's these two reactions that I added together. So if I want the enthalpy of this reaction, I'm going to simply add up the enthalpy of those two known reactions that I used to sum up to get that unknown reaction. All right, so in this case, the first one was negative 465. And then I'm going to add 42. What is that? 23, negative 423. So my overall reaction here that I had, my unknown reaction, I can calculate that enthalpy value, again, by summing up those two knowns. All right, so in the same way that we summed up these two chemical reactions in order to get our overall reaction here, the reaction we were trying to study, we can sum up our two chemical reactions in order to get the enthalpy here. All right, so this is a little cluttery. Let's kind of simplify real quick. Okay, so let's say we have this unknown reaction A plus 2C gives us D. And we don't know the delta H of this reaction. So we have these two known reactions. A plus B gives us C. And 3C gives us D plus B. All right, and I just kind of came up with these, but bottom line is we do know the delta H of this first reaction and the delta H of this second reaction. Okay, take a second and sum up these two known reactions here. Okay, so if we do it A plus B plus 3C on my reactant side, gives me C, D, and B. And now we need to cross out everything that appears on both sides of this chemical equation. Well, we combine, but then we're going to cross out. There's nothing to combine. So we get rid of B and one of those C's. Okay, so we have A plus 2C gives us D. And likewise, we're going to do the same thing with our known enthalpy values. We're going to sum them up. So the delta H of this overall reaction is just equal to the sum of those two steps. Okay, so when we sum these known reactions together, we can just sum their enthalpies to get the energy change, the amount of heat that's absorbed or released by that overall reaction. All right, so let's continue with these kind of simplified versions here, and then we'll complicate it with a real example. All right. So let's say that we know again that A and B will combine to make C. And we know this delta H. Let's just put a number on it. We're going to call it a delta H of 4. Nice, easy number to work with. And we also know that B plus D gives us C. We know that delta H value. We're going to call this -2. So these are two reactions that we've studied before. But now we have this unknown reaction. Where A is being converted to D. And we want to know the delta H of this reaction. All right, if we sum up these reactions as is, we're not going to get this unknown reaction. We're not going to get this overall reaction, right? If we sum these up as is, we'll get A plus 2B plus D gives us 2C. That's not what we want. We're not after that. All right, so how can we use these known reactions? How can we combine these in such a way that will leave us with our overall reaction? All right. Well, what we need to do is we have A on our reactant side in this first, or in our unknown reaction, and A on our reactant side in our known reaction. All right, cool. But if I look at my second reaction, I have D on the reactant side, but D is supposed to be a product. All right, so let's flip this reaction. So we're going to call this reaction 1, and we're going to call this reaction 2. We're going to leave reaction 1 alone. All right, but now we're going to flip that second reaction. So what do I mean by that? I mean I'm going to write my product of that second reaction first. And then my reactants, C, B, and D, are going to appear on the other side. All right, so now I'll take a second and combine our reaction here. If I combine these two, I get A plus B plus C gives me C plus B plus D. So what can I cancel out here? I got C on both sides. What else? I got B on both sides. So what I'm left with here is this reaction, A being converted into D. Is that the reaction that I'm trying to study? Cool. So I combine these two reactions to get my unknown reaction, and I need to do the same thing with my enthalpies. Now I can figure out the enthalpy of that unknown reaction. The problem is that I flipped this second reaction here, right? So I know that in this forward direction, B is going to combine with D to create C, and that will release 2 kilojoules. Well, if it goes the other way, that reaction will just absorb 2 kilojoules. So I'm going to need to flip my delta H as well. What do we mean by that? I mean I'm going to multiply it by -1. I got to change the sign. If energy is going in one direction, that means that it's being absorbed in the other direction. So now my delta H of that second reaction that's been flipped is equal to +2 kilojoules per mole. So when I sum this up to get my delta H of my unknown reaction, I get a value of positive 6 kilojoules per mole. All right, I had these two known reactions I'm trying to combine to get my unknown reaction up here at the top. But if I combine it as is, that won't give me that unknown reaction. I got to flip that second reaction. And when I flip that second reaction, we'll combine to get our unknown reaction. If you flip a reaction, that means that you have to multiply that delta H by -1. All right, so let's do another example here. We got these two known reactions. Again, I know the delta H of these two reactions here. Again, let's put a number on it just so we have something to work with here. This one will be 12 kilojoules per mole. And the other one will be -35 kilojoules per mole. All right, and I want to use these two known reactions to study this unknown reaction. Where 2A plus 2B gives us D. And this is what I don't know here. All right, so again, we'll call these reaction 1 and reaction 2. If I combine these together as is, are they going to create my overall reaction? No. All right. But if I look, all my reactants are on the right side. I got A and B on my reactant side up here with my unknown. I got A and B on my reactant side on my known. So I don't want to flip that reaction. That's not going to help me out. Likewise, if I look down here, I have D on my product side and D on my product side. So I don't want to flip that reaction. That's not going to help me out. So then how am I going to combine these two reactions to get me my overall reaction? All right. Well, if we look, I have 2 A's and 2 B's in this overall reaction, in my unknown reaction, and only 1 down here. So what if I just double that known reaction, that first known reaction? All right. Importantly, when I do that, I have to double everything. I have to double all my reactants and all my products. All right. So we're not going to do any flipping this time around. Instead, what we're going to do is we're going to double that first reaction. Multiply that whole thing by 2. This gives me now for that first reaction 2A plus 2B gives me to 2C. All right, so then if I take my second reaction here and add that in there, everybody take a second to simplify here. Let's add these two up. All right, we can see those two C's will cross out, and so I'm indeed left with my 2A plus 2B gives me my D, right? My overall unknown reaction that I was looking for. Cool. So how do we get the delta H of this reaction? Okay, again, we want to use those known values. All right, but remember I had to double that first reaction. So what do we think I should do to my enthalpy value for that first reaction? Double it, right? Exactly. If I carry out this reaction with just one of A and B and it releases 12 kilojoules of mole, well, if I perform the reaction with twice as much, it's going to release twice as much energy. So the delta H of my doubled reaction, I'm also going to multiply by 2. All right, so now this becomes delta H1 equals 24 kilojoules per mole. I didn't touch the second reaction, so that's going to remain that negative 35 kilojoules per mole. All right, which means that when I sum these up, I'll get an overall delta H, or a delta H of this overall reaction equal to negative 11 kilojoules per mole. All right, so this method of combining these known chemical reactions in order to find the enthalpy of an unknown reaction. Importantly, two tricks that we use here when combining chemical equations. We can flip our reaction. Right? So if A to B has a delta H of negative 2, then when I flip, B goes to A, and this would have a delta H of positive 2. All right, so flipping a chemical equation, means that we multiply that delta H by negative 1. All right, the other thing that we can do, the other way that we are going to have to sort of manipulate these to combine is to multiply by some constant value. All right, so if A to B has a delta H of negative 2, that means that N times A going to N times B has a delta H of N times negative 2. And N can be any constant value. All right, in our previous example, it was 2. We doubled it. Maybe you need to triple it. Maybe you need to cut it in half. All right? Whoops. Okay, but these are these two tricks that we're going to use to combine these chemical equations. All right, so let's play this game now with an actual chemical equation, looking at chemical formulas, all that jazz. All right. I'm going to give you this overall equation. This is my unknown chemical equation that I'm trying to figure out, my unknown reaction. And honestly, for the sake of just not cluttering this up, I'm going to leave out my state symbols. They're all gases, all right? But just for the sake of not having too much clutter going on here, we're going to be lazy and omit our states of matter here. All right, and I don't know what the delta H of this reaction is. All right, this is the one that we're trying to study here. What we do know are the following. So here's my first known reaction. And I know the delta H of this reaction. That's why it's going to be useful. All right, is negative. Whoa. Go away. All right, and then we have a second known reaction here. All right, so looking at these two known reactions, I want you to figure out how these can be combined to create my unknown reaction up top, and then you'll use that same strategy to combine your enthalpies to get our enthalpy of our unknown reaction. Pay careful attention to what's on the reactant side and the product side of your unknown reaction, your desired reaction, and what's given. All right, there's a little bit of trial and error involved. All right, combine them as is. That didn't work. All right, let's flip one of these around, putting these reactants on the other side. Combine them again. All right. There's not really one way to do it. You'll get better at it as you practice. All right, but we're trying to combine these known reactions 1 and 2 to create that unknown reaction. All right, so let me show you how my logic is when I'm going to approach something like this. All right, I'm going to go in and find all of these things that appear in my known reaction down here in my unknown reaction, down here in my known reaction. Let's just find where everybody is here, and I'm going to sort of color code so we can see what's what. All right? So I just color coded the symbols of everything that was in my unknown reaction and where it appeared down here in my known reaction. All right? If I look compound by compound, the first thing I'm going to notice is there's a lot of red down there. I got red in both of these two known reactions here. All right? So just by looking at that, it's going to be hard to tell what's going to go on here. So if I see something all over the place, just like when we were balancing our chemical equations, I'm going to ignore that for right now. I'm going to go to something else to see if I can't narrow down what's going on here. So let's just get rid of this red for right now. We'll go back to the NO2s. All right? If I look at my CO, the only place that carbon monoxide appears in my known reactions is down here, but it's on the wrong side. Likewise, if I go to my CO2, the only place that this purple appears in my known reaction is down here. But again, it's on the wrong side. So what am I going to have to do to my second known reaction here? I'm definitely going to have to flip it. I might have to multiply it by 2 or whatever it may be. I don't know. I'm not done with it. But I know that in order for this to work, I have to flip that second reaction. That's the only way to get carbon dioxide on the product side and to get carbon monoxide on my reactant side. All right? If I look at the orange here, my orange, NO, only appears on the product side in one of these two known reactions. So am I going to have to flip that first known reaction? No, that would mess everything up. It would put that NO on the wrong side. All right? So I know I'm going to have to flip reaction 2 and not reaction 1. All right? The other thing that we can notice here is that there's one of these species that I didn't color at all up here. And that was that NO3 rather. This appears in these two known reactions, but it doesn't appear anywhere up here. So what does that mean is going to have to happen when I combine these two known reactions? It's going to have to cancel out. All right. So first of all, let's back it up. Let's just flip that flip that second reaction. So I'm going to leave that first reaction alone. And then I'm going to flip that other reaction. And again, I need to get these blues to cancel out here because they don't appear anywhere in my unknown reaction. All right? If I combine together right now, they're not going to combine correctly. So what do I have to do here? How can I combine these in such a way that everything will cancel out and leave me with my overall reaction? Okay, so if I multiplied this bottom reaction by 2, I would end up with 2 times this unknown reaction here. So I don't want to touch the second reaction. I instead want to multiply that first reaction by 1/2. Right? I need to cut everything in here in half. Oops. So that means I have 2 NO2s and 1 NO3 and 1 NO. And what am I going to have to do to my enthalpy as well? divided by 2, multiply it by 1/2. So negative 157 kilojoules per mole. All right, so for my first reaction, I had to multiply it by 1/2. My second reaction, I had to flip. Now if I combine everything together, I will get my overall unknown reaction. So I can do the same thing with my enthalpy values. I can combine them together to get my enthalpy of my unknown reaction. What is that? 112? Cool. Mental math is hard. All right. Cool. So we need to figure out how to take these known reactions and manipulate them. And we got two tricks. We can multiply them by some constant value. So we multiplied that first known reaction by 1/2. Or we could flip them to combine. And when we flip, we have to flip the sign of that enthalpy value. Combining these known reactions, we can use those known reactions to study our unknown reaction. All right, and we'll do the easier way using our constants page next time. All right?